Well, hello everyone. Today we'll talk about the tension steel members. This is chapter 9. So to go first, before solving any problems, I would like to share with you some information about the steels, their properties, and some other attributes, and the reason why we use these steel element as a structural elements in a building. So first, the steel structures are consist of typically frames, cables, and trusses and plated structures. The I shapes typically consist of two pieces of a flange horizontally and one vertical piece, which is the web. Now, the classification of these sections comes like by W shape, M, S, and HP shapes, and they vary from classification to classification by their thicknesses of their flanges. For a designation like W14 by 68, for instance, the 14 represent the width of the flange, which is 14 inches, and the 68 is the weight of the item or the element, which is 68 pounds per foot. Now, there is other standards that we typically look at as well, like channels, C and MC, and angles like L, and T's like WT, MT, and ST. Since this topic is about tension steel members, for compression members, though, we typically use tabular shapes. So rectangulars and square sections are represented by the letters A, H, S, S. And for rounded tubing, you have HSS grade 42, and for pipes, grade 35. Now for the, we still in the properties of steel, and for yield strength of steel, also known as the modulus of elasticity, the value, as you all know, it's a 29,000 KSI. Now this value represents the stress-strain relationship of all the grades are similar. Now, why do we prefer steel as a structural element? Because of its ductility, excuse me. So this is a very good attribute of a steel that it has, because it withstands, it bears a lot of stress, high level of stress without failure. And even if it does fail, then it shows signs of failing before the complete failure, which is the rupture. Unlike brittle materials where they rupture before any sign of failures. So having a steel in buildings like a structural element is very beneficial. Now, as far as the Unified Design Specification, we have the American Institute of Steel Construction, AISC, and that kind of, this organization unified all the codes into 4 types that we typically design the steel for. The first one is the allowable stress design, ASD. The second is the load resistant factor design, which is LRFD. The third is single angle members, and the fourth is the hollow tabular structure sections. What we typically use the first two, which is the ASD and LRFD, and we design according to those. Now, as far as the limit state of design, we are expected to stay within the limit of the design that are expected or enforced without exceeding them. So in other words, we design against 3 types of failure modes. The first one is yielding, second is buckling, and the third is the serviceability limit states like deflection and slenderness. So we design against those mode of failures. Now, as far as the limiting states for those tensile members and connecting elements, we look at the tensile strength, the shear strength of connections, and the block shear strength of connection along the shear or tension failure path, and we'll study the three of them in details. So when it comes to the tensile strength, we look at two scenarios and we choose the lowest value from them. The first, at the yielding at the gross section, which is P sub U equals 0.9 times FU times AG, or the rupture at the net area, which is P sub U equal 0.75 FU A sub E. So PU stands for factor design tensile load, as you can see. The FY is the yield strength of steel, and FU is the ultimate strength of steel. The AG is the gross area, and AE is the effective area. It's imperative that we have to be familiar with each letter, each abbreviation and letters here, because we're going to use them intensively. Now, what is shear leg? Shear leg is when a portion of a member is not fully connected, like a leg of an angle section. The unconnected part is not subject to a full stress. So the shear leg is the U, as you can see here. Let me get my pointer. As you can see here, this is the shear leg. So the area, the effective area, A sub E, is the A sub N, which is the net area, times the shear leg. And we'll see what does that mean exactly. So for the net area is the thickness times the net width. And the net width is the summation of the width of the holes for bolt that is subtracted from the gross width. And the hole width is taking us 1/8 of an inch greater than the bolt diameter. So what does all this mean to us? Let's look at this diagram here. And let me grab my pen. So imagine if we have a force pulling in this direction and a force is pulling in that direction. And we have these two pieces of steels are connected together. This one and this one here. They connected it through two bolts, staggered bolt, zigzag. So imagine we have multiple of them, but for just the purpose of the example, we took here two. Again, we have two forces are pulling in this one, this direction, and this direction. In other words, most of your stress actually it's applying here and here on the bolt, and here on the bolt as well. So this is B, which is the width of the flange, the width of the piece of steel. Here's your thickness, and S represents the longitudinal distance between the two bolts horizontally. And as you can see, it's within the direction of the forces, like horizontally going in that direction. And then you have G, which is the transverse direction, which is perpendicular to the forces, the distance between the two bolts. Remember, the G and S are measured from the center to center, center to center. And then you have H here, which is the size of the hole. Now, for an angle situation, like as we see here, our bolts are in two different angles. So then your G, it's from the edge of the angle to the center. So as here, but the way we find it is G equals G1 plus G2 minus the thickness. So now, to start with this example, let's look at this example in the other recording due to the time constraint.